So I'm going to talk about CUDA and libraries. OpenACC will be covered this afternoon. So again, first I'm going to cover CUDA programming, and then GPU libraries, and do ask questions. Our favourite slide, just showing libraries and language extensions. We saw this slide before. I just want to quickly go over it again. So CUDA is available in C, C++, Fortran, Python, MATLAB, and other languages. I'm going to be talking about CUDA Fortran in this talk. Some of the slides I did convert from CUDA C, so that there's a small chance that some C syntax will have leaked in. Apologies if that's happened. If I notice it, I will point it out and explain the relevant Fortran syntax. I think I caught everything. Again, CUDA Fortran is based on industry standard Fortran. It's a small set of extensions, and it's got a straightforward API to manage your GPUs. So I'm going to cover 4 concepts in CUDA programming. I'm first going to talk about heterogeneous computing. So I'm going to go over the memory movement again. I'm going to talk about what it really means to have a GPU attached to your CPU. I'm then going to describe how you get an application to run on the GPU. That's before we go in parallel, just having something running and going through it. We'll then change that to run in parallel on the GPU. And I'm then going to have 3 or 4 slides of extra information. So the extra information will largely be for people who are interested in exploring CUDA further. It won't explain the more advanced topics, more point them out and mention them, and say what you might want to investigate into in the future. So it's not enough time to do a complete deep dive on CUDA programming, but I can point you in the right direction for specific topics. So we're going to start with heterogeneous computing. We have our CPU, we have our GPU. We've seen this before, and that's all I wanted to talk about heterogeneous computing. The PCI bus is a problem. We have code that runs on the CPU and code that runs on the GPU. So now we want to run on the GPU. GPU computing is about massive parallelism. I've explained the hardware previously, and it should have been clear that to get good performance out of the GPU, you need a lot of parallelism. 10K, 100K, a million threads. A simple case, which has a lot of parallelism, is vector addition. So C equals A plus B. Each element of A, B, and C can be, or each element of C can be calculated independently using one value from A, one value from B. If our vectors are long, so we can pick our vectors to be arbitrary size. If we've got a 10 million length vector, then clearly we have a lot of parallelism. If they're 8, like my diagram, then we don't. But in these examples, we will have a lot of parallelism. There's a generic operation for what we're doing here. It's called AXP, so you'll hear about SAXP and DAXP, so single position and double position, and that's AX plus Y. So I've used slightly different terminology, and I don't have AX, I just have X, so it's X plus Y or A plus B. And you'll see it in libraries. I think it's covered in QBLAS, although it tends to be a fairly simple operation. It's the sort of code that OpenACC will do very well, and writing in CUDA is quite trivial. So again, let's have our standard Fortran for a vec add, so a vector addition, or X plus Y. Again, it's not very complicated code. We take 3 arguments in, A, B, and C. A and B are inputs, C is an output, and we also take in N, which is an input, which is the length of our vectors. Then we iterate over the length of our vector, doing ci equals ai plus bi. And we call it, just as vec add CPU. This works on the CPU, great. Now, executing on the GPU. I suppose I've already covered this, but just to reiterate, we have attributes global to tell the compiler we want to compile for the GPU. Other attributes are available for different compilation targets. We have value to pass n by value, not a CUDA-specific syntax for Fortran 2003, but particularly useful so that n isn't passed by reference, which is not something we want to do because it's a scalar and it's only read from. And finally, we have our GPU launch command. In this case, we have 1. So this code will execute on the GPU. However, it won't execute in parallel on the GPU. We are launching 1 times 1 thread. So that's 1 thread. So we still have our do loop here. We still have a loop over n elements. This code will not be fast. It's not exploiting any of the parallelism of a GPU, but it is going to do pretty much the same instructions as a CPU will do. It's the minimal changes required to actually have something that runs on the GPU. No parallelism there.
Why do you worry about n? It's a scalar. Is it because it has to be moved into the GPU, or the control logic is that information has to be passed in some respect in the kernel? Why worry about n? Passed by value instead of passed by reference. It's not modified here.
It's a more efficient argument passing method.
So
the vectors are 1,000,000 or something. Why worry about something that's a scalar?
So it may be the newer versions of CUDA Fortran do it differently. But when I first looked at CUDA Fortran, it would create a explicit memory copy, an explicit 4-byte memory copy for n, and that would then take up some time in the latency of the copy and the CPU overhead for the copy before you call the kernel.
To eliminate any kind of hosted device communication.
So you don't have to, actually.
Even if it's just 4 bytes.
4 bytes, but there's a startup cost for that.
Yeah, so there's quite a latency cost, 5 microseconds, 10 microseconds for moving across 4 bytes. But a vector addition, even quite a large vector addition, will take order of magnitude 10, 20 microseconds. So this latency cost of the memory copy can be significant. It depends on the length of the vector. If you've got
passed by value, then you're saying there's no host-to-device communication then for that.
So it gets tied into the kernel launch. Yeah. So the information is passed host to device, but it's combined with the thing that launches the kernel to the GPU. So it's passed as an argument. Now, it may be that the value is not necessary in current version of the CUDA Fortran compiler. It used to be required for performance. I don't know if you can.
It's the same.
It's the same. Okay. So you should still pass scalars by value if you can.
In C, you would not have to do anything.
No.
Always pass it by.
Yeah.
Because you control it directly in the signature of the function.
Exactly. So in C, yeah, you wouldn't do anything. So I've described previously how host and device, so the CPU and the GPU, had their own different memory spaces. Now, I've also said that you want to minimize the copying over the bus connecting the GPU and the CPU. So we have to have a way of declaring that our memory is on the GPU. We have to say that this buffer resides on the GPU. Right now, there's 2 ways of declaring memory that the GPU can read. And these are applied using Fortran attributes similar to value. So one of them, and this is fairly new, is the managed attribute. The managed attribute provides you with a GPU and CPU readable data structure, region of memory. That's quite convenient. However, it does mean that the locations of the places where the data is moved across are abstracted away from you. You don't get to control them. Now, this means that if you are having problems with this PCI bus speed, you don't get to use your knowledge of the algorithm to work around it. So it's taking some of the control out of your hands. There's a few extra steps you need to do to use the manage attribute to make it safe. But in general, using it requires fewer lines of code and simpler code.
Does the managed code work name that you've chosen for the shared memory between the shared memory space?
So it's not a physically shared memory space. It's a yeah. So from the programmer's perspective, the GPU and CPU memory spaces are as one. There's a few limitations. So, for example, you can't declare more than the GPU's memory size of managed memory. But from the programmer's point of view, you don't need to worry about the physical location of the memory when you're using the manage attribute.
The CUDA runtime looks after
The CUDA runtime looks after it.
Data back and forth across the bus.
Exactly.
Who's looking at it?
Exactly. So it's handled by the driver. It's going to right now. It's a useful feature to know about. It's going to become much more performant in future architectures, and it's a nice way of getting your code working fast. If you don't have any problems with data movement, you'll get much neater code.
It surely has issues of cache consistency and between the CPU and the GPU. No?
You will end up moving more data. You'll end up moving it at times you don't necessarily want to move the data. So it's convenient.
Crashing around between CPU and GPU.
Things don't get moved if they're not accessed. So if you're accessing it on both the CPU and the GPU, then yes, there will be data transfers going on, and it might not be efficient. But as I said, it's largely for ease of use rather than necessarily power programming. If you want full control over where your memory is and what it's doing, you use the device attribute, which provides you with GPU readable memory, which you cannot touch on the CPU. So touching it on a CPU would be a segfault. And that, using the device attribute, allows you to manage when all your memory is moved across, but takes up a few more lines of code. Both available. Here is an example using managed memory. So the line we've added, sorry I haven't highlighted it here, but it's just there, managed. So we have a real managed arrays. We then call our VECAD GPU from before. And one thing we have to do with managed arrays is we have to synchronize our device before we touch them on the host. So we need to, GPU calls are asynchronous. So when we call VECAD GPU, this is asynchronous. It will return immediately while the GPU processes. So you can carry on processing on the CPU. Now it's an error to touch memory, managed memory, which is currently being processed on the GPU, on the CPU. So we synchronize after calling our vector addition. That asynchronous behavior is a useful thing to know about because it's not something a lot of programmers are used to. Most people are used to calling something and then being returned control when the process is finished. GPU launches are asynchronous, and you have to explicitly synchronize.
Asynchronous call going on, or multiple ones with different handles?
You can have more than one. Yeah, so I could call VECAD GPU on one set of data, then VECAD GPU on another set of data, and both would then be asynchronous. So we would then return control to the CPU thread.
And can you synchronize against each one separately, or do you have to just wait?
Yes, so you would be using something called CUDA streams, which goes into another argument between our angled brackets. So there's further optional arguments, and then you can synchronize a particular stream. So you can launch work to many different streams and synchronize between them.
Do you have to synchronize also if you call QGlass? Or is there implicit synchronization?
If you're calling QBlast with managed memory,
okay, then
I would synchronize. In general, the asynchronous behavior is not something that can cause a problem. unless you're using managed memory. So if you, for example, you were using explicit memory copies, the memory copy would wait until the execution on the GPU had finished. It's really something that's either required when you really do know you need it, or with managed memory. In general, it's not something you need to do. It's useful for error checking. So istat will contain an error code, which may or may not be useful if you're having problems.
When you say it's an error, do you mean that it's actually detected as an error, or is it undefined behavior? Like, how does it?
It will cause a segmentation fault. So that is, if you access managed memory on the CPU while the GPU is touching it, it will cause a segmentation fault. It may be that this restriction's lifted in the future, but right now that's where we are. And the other method is using the device attribute. So again, I've not highlighted it, but it's just there. So we've replaced managed with device here. And because we now have memory we can't touch on the CPU, we need to declare two copies. We need to declare a GPU copy, so _d _device, and a CPU copy, _h _host. This is required because we have literally two copies of the data. In CUDA Fortran, copying the data is actually very easy. We can just use this explicit assignment. We can say the device memory is equal to the host memory. And that will call a copy and copy the memory to the GPU. There are also explicit API calls you can use. So in CUDA-C, you would use an API call, for example, CUDA mem copy. And there's also asynchronous versions of that, CUDA mem copy async. So there are API calls you can use to copy memory. In C you have to. In Fortran we have this very nice syntax of just being able to do a single assignment. So what we do here is we copy A to the GPU, we copy B to the GPU. After initializing them, we do our vector addition, and then we copy C from the GPU back to the host. Notice we don't need the device synchronized because it's implicit with the copy.
Sorry, would it work for derived data types? Would it copy all the members of the derived data type?
The what data type, sorry?
Would it work for derived data
Oh, derived data types. So if you have a derived data type with a member not declared as device, then, I see what you mean. So you mean the assignment? Yeah. I think you need two types, one with it declared as device, one with it declared not as device, and I think the assignment would just work. Do you know, Michael?
The deep copy.
I'm trying to remember, and I don't know the answer to that question. I'm embarrassed to say.
So we're not sure.
Do it, but it doesn't always work.
Yeah, you may have to go through the members explicitly. Oh, it might just work. I'd have to test it.
Excuse me. So the call to vector is asynchronous,
Asynchronous, yeah.
and that means that the equal operator has an implicit block there.
Yes. So it knows that CD resides on the device and therefore will block will block until all operations are finished. There are ways of doing it.
Operations.
All GPU operations are finished. There are ways of doing it asynchronously, using streams, and I think you'd have to explicitly call an API function, CUDA mem copy async, to do it asynchronously. But the default is blocking behavior on the copies.
So, okay, maybe what I'm trying to ask is, if I send multiple asynchronous calls, and I do then a copy. Obviously, you do multiple asynchronous calls on different data.
Yeah.
And I do a copy. Is the block only on that data, or is the block on all the operations of the GPU?
It's on all the operations. Well, it could not be otherwise in the general case, because you don't necessarily know which data a kernel is going to operate on. There's lots of indirection you could have which would mess it up. But you can do it asynchronously, so you can call CUDA mem copy async, and that is non-blocking. So if you want to do multiple asynchronous calls to the GPU, asynchronous copies, it's possible. It just requires a slightly more advanced way of writing your code. You can no longer just do a simple assignment.
So can you do continuations? Can you say, call this synchronously, at the end, do the copy?
Yes. Yeah. So there are things called CUDA streams, and each stream is sequential, but they can run in parallel with other streams. So operations pushed to a stream will happen sequentially, but there are many streams.
So you can queue the copy at the end?
Yes. Okay, so that was running on the GPU. We have our simple code, copies data across the GPU, or uses managed memory to copy data across the GPU, and does a one-threaded run on the GPU. Well, that's no good. We don't want to do one thread. We want to do lots of threads, because one thread is not going to give us good performance. So first, I would just like to mention some things about how a GPU is laid out. So we know that a CPU has many cores. A GPU has many cores as well, but above the cores, there are things that are perhaps more analogous to CPU cores, and these are called streaming multiprocessors. So typically on a GPU, you'd have maybe 10 or 15 streaming multiprocessors, but it varies somewhere between 1 for the embedded GPUs to 24 for the largest GPUs. So you have many streaming multiprocessors on a GPU. Each streaming multiprocessor has many cores. So on the Kepler architecture, there's 192 cores per streaming multiprocessor. That number may go up or may go down with future architectures. So another architecture we have has 128 cores per streaming multiprocessor. Typically, it's a multiple of 32. Each SM, each streaming multiprocessor, also has its own private memory, so its own sort of scratchpad space, which allows cores within an SM to talk to each other. So you can communicate between threads operating on different cores within your SM. I'm not going to talk much about that private memory. It's going to be a topic of one of the extra information bits at the end. It is useful for some algorithms, but not for our vector addition. So in CUDA, we have a sort of a hierarchy of terms. It's much the same as in the hardware. So in the hardware, we have a GPU. In the CUDA, we have a grid. So these terms are partially based off graphics. So if we have a 2D image, we have a grid of cells. Or a grid of, actually it's a grid of blocks, we call them. So each streaming multiprocessor is where a single block resides. So you can have many blocks on a streaming multiprocessor, but a block cannot span multiple streaming multiprocessors. So there's grids on the GPU, blocks on a streaming multiprocessor, and then there's threads on cores. So there are many cores per streaming multiprocessor, and typically you want more than one thread per core. So that the GPU works through pipelining and oversubscription. So you want many threads per block, many threads per core. So a streaming multiprocessor might have 192 cores. You probably want 3 or 4 times as many threads on that streaming multiprocessor. The exact way that things map together, how many threads you'll get per streaming multiprocessor, is quite a complicated topic. I'm not going to go into it. But if you want to find out more, then there are resources available, which I will link to later. But the core of this is that we need many blocks, many CUDA blocks to map to our many SMs, and we need many threads in each block to map to our many cores per SM. When we're writing CUDA, we write it from the perspective of a single thread. Now, we have our blocks and threads, so blocks contain threads, and you'll have seen something like this in my earlier presentation. This is how we calculate which element to work on from our blocks and threads. So let's say we have 8 threads per block. Typically, that's a very small number. Typically, you'd want 128, 256, 512 threads per block. Let's say we have 8 because it fits on the screen nicely. In each thread we have some variables that we can read from, some constants we can read from, I should say. And these are, two of them are block IDX and thread IDX, so block index and thread index. In Fortran these are one indexed, so it starts at 1. In C they start at 0. And from these two numbers, and knowing how big a block is, we can calculate a global index for the thread that we're currently in. Handily, we also provide block dim, which is the dimension of the block. So in this case, we have block dim threads per block. Block dim is 8 in this case, 8 threads per block. And we can calculate a unique index for each thread from this equation. We take our index, we minus 1, we multiply it by the dimension, we add our thread index. So this turns into 1, 2, 3, 4, 5, 6, 7, 8. 2 minus 1 is 1, times 8 is 8. 8 plus 1 is 9, 10, 11, 12, 13, 14, 15, 16. And it carries on. So we get a unique ID for each thread from this calculation. Because each thread has a unique value of, well, a unique combination of block IDX and thread IDX. So using that, we can work out where we are, and in one line, quickly calculate our thread index to operate on. So I've changed this.
Did the thread indexes start at 1 in Fortran rather than 0?
It starts at 1, yeah. In C they start at 0, in Fortran they start at 1.
In CUDA they start at 0.
CUDA C they start at 0, CUDA Fortran they start at 1. Yeah.
Right.
So that's, I mean, indices in general in Fortran start at 1. So. It's expected. So in C, for example, block IDX would start at 0, so you wouldn't need this minus 1 as it happens. But it's details really. It's something that if you're transitioning between C and Fortran a lot, you might get caught out by, but you get off by 1 error if you're transitioning between Fortran and C a lot anyway. So it's another thing to bear in mind if you're working in C a lot. So we have our unique index. We also have bounds checking, as I mentioned before. We have the ability to launch too many threads, and this is safe if we do that, because if our thread index happens to be larger than the length of the array, then we don't do any calculation. One more thing I'd like to say about blocks, grids, and threads is that I've used one-dimensional indices. In general, you can calculate everything you want from the one dimension, but some problems have a natural dimensionality to them. So, for example, an image problem has naturally 2 dimensions. And these block shapes can be 2D or 3D. In general, that's sort of for ease of use. It doesn't add any... It can simplify the indexing calculation, but you can calculate everything from a single x dimension. So it's mainly as a simplification if you have a problem with higher dimensionality than 1. It's simpler just to stick with x for now. So we've seen our host code copying the data across before and this before. The thing we've changed here is we've changed the thing between the angle brackets. So the lines that have changed we've added use CUDA4. So we've used the CUDA Fortran module. That defines the type dim3, which we've then declared block size and grid size. And then we've initialized block size and grid size to be 1024 threads per block and 1024 blocks per grid. Now you'll notice that I'm using 1,000,000 elements, and 1024 times 1024 is slightly over 1,000,000. So this is where we use our bounds checking. It's just a bit convenient. I could have 1,000 by 1,000. It's I guess you can't always find two numbers that multiply together to give a third number. And the shapes of these blocks and grids can affect performance. So sometimes you do want to go slightly higher than the number of elements in your array.
Can you go back to the previous slide? It's this block IDX. So these are things we don't touch.
No, they're constants.
Sorry?
They're constants.
They're constant.
Yeah, and so the attributes global tells us that we have these constants defined.
And that depends on whatever hardware
so this depends on your launch parameters. So they're constants per thread. So each thread has a unique value of this constant. That you cannot write to them in the thread. So each thread has each thread has a unique combination, I should say, of block IDX and thread IDX. So this picture kind of explains it. These 8 threads, so this is say 32 threads. These 8 threads have block IDX 1. These have 2. These have 3. These have 4. And this is the thread IDX here: 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're writing from the perspective of a single thread, and each one has a unique combination of block IDX and thread IDX.
I guess that at one stage someone will have defined the block dimension. No?
Yes. So this is why we have block dim here, and this tells us our dimension. So we can multiply by the block ID by the block dim to get our offset into our current block.
That comes from the launching parameters?
That comes from the launching parameters. So we've here defined our block dim to be 1024, and our grid dim to be 1024 as well. So and that is put in there, and we can set that to be whatever we like. That's dynamic. So I could change that to be 8, but then I'd have to make sure that the total number of threads was larger than n.
And the one would be when you have the y and z dimension in your blocking.
Yes. So these are the y and z dimensions which I've set to 1.
And so the values you pick, like the 1024, is it independent of the hardware?
So there is a maximum block size. There is a maximum grid size, but it's very large. There is a maximum block size. So on current generation hardware, you cannot have more than 1024 threads in a block. So that's total threads in a block. So I couldn't double this and half this, because then I'd have more than 1024 threads in a block. But I could double this and half that. There's also certain performance things. So having it as a multiple of 32 is convenient, and due to hardware design, and there's how many blocks you can fit onto a streaming multiprocessor will depend on this number. So a streaming multiprocessor may be able to fit 3 blocks of size 512 or 1 block of size 1024. In general, you want more threads on a streaming multiprocessor. That's known as occupancy, and again, I don't really have time to go into it in too much details, but different kernels will have different levels of occupancy, and different block sizes will work best.
You said you can to make sure you provide enough threads to handle all the situations of the loop.
Then it doesn't calculate the end of the loop. So
there's no error.
So if this was 1 and this was 1, then this code would only calculate block IDX equals 1, so 0 times whatever that is, 1, I guess, plus 1. So it would only calculate for index equals 1. So you have to make sure that you're launching as many threads as you need.
But isn't it so typically if you go to the next slide, so you actually embed this n into the tree calculation?
Yes. So normally you'd calculate this from n. I've written it myself. Yeah. So normally you'd calculate it from n. We've turned this from a 1 thread, 1 block code to a 1024 threads, 1024 blocks code. and we're going 4,000 times faster. Is that right? Yes, that's right. So this is milliseconds, 241 milliseconds, 66 microseconds. So you need parallelism. Running a GPU code in serial or anything near serial is going to give you much, much worse performance than running in parallel. It's a 4,000 times speed up from running in parallel. I looked at these in a bit more detail, and this is going fairly close to the fastest vector addition you could run, maybe 10% off, but just that simple code is pretty good. There are a couple of tricks you can do, which I think OpenACC, for example, would do, and I think an OpenACC version of this code would probably go a little bit faster than 66 microseconds. So the extra information, this is the bits I'm tagging onto the end of this CUDA programming section, which if you're interested in CUDA programming, you might want to investigate separately. So the first one is this shared memory. I mentioned an SM has its private region of memory. That's about 50K, 48K maybe, kilobytes, which is known as shared memory. It's accessible to all threads within a block and allows them to cooperate. So you can efficiently pass, using the shared memory, you can efficiently pass data between threads in a block. So there's a limited amount of cooperation you can do here without having to go back to main memory. And typically, if you're writing a high-performance algorithm, shared memory is one of the things that really will tune it up. So, for example, a matrix-matrix multiplication uses shared memory quite a lot. There are synchronization primitives, so you can synchronize all threads within a block. You can't synchronize across blocks, only threads within a block. Divergence and branching. So some of you may have heard that GPUs don't like divergence. It's true. They don't really like divergence. They can tolerate it, but it's not something they enjoy. There's a couple of rules that if you stick to, you won't have any problems. So the first being memory divergence. So ideally, a group of 32 threads should access a contiguous 32, 64, 128 byte memory space in the same instruction. Have a good example here. We're each accessing from thread ID X. If we have, say, a large block size, then thread 1 will access the first element, thread 2 the second, thread 3 the third, etc. A group of 32 threads would then be accessing a contiguous set of memory. A small stride is okay. So a stride of 2, for example, won't be too bad. But in general, you want to be nice and aligned and adjacent, contiguous. Bad would be accessing with a 1,000 stride. So thread 1 would then access the 1,000th element. Thread 2 will access the 2,000th element. They're all pulling in data from different parts of the GPU memory, and that's going to be inefficient. If you do have a code with a stride, you can do a transpose using shared memory. So you can pull data in a contiguous fashion and then use this thread cooperation to do a transpose. So there are ways of getting around large strides without having to reorganize your data, but it's something to avoid. You don't want to be reading with a stride. The other type of divergence is instruction divergence. So it's not the same as a vector instruction on a CPU, in that the GPU will handle branches quite tidily. Typically, if you have a branch where either A or B are taken, and there is divergence within a group of 32 threads, it will calculate all the threads that take path A, then all the threads that take path B. So a small amount of branching is usually okay, especially if you have an if statement with no else statement, because then you're not really paying any penalty at all. Large branching, so if you have a select statement with 32 possible outcomes, each of which has a 32-way select statement within, then every thread's going to potentially be going in a different direction, and you're going to have some performance problems. That's quite a pathological case, though. Not many codes look at all like that. And finally, as I've been saying, as I've been going through, I'm on the tip of the iceberg here. There's a lot of GPU programming with CUDA is is what you use if you want to get the best performance. And to get the best performance, you have to understand quite a lot about the system and about what the programming language can do. I've linked two programming guides here, the CUDA Fortran programming guide and the CUDA-C programming guide. Both are good references and both cover some more advanced topics, including, for example, shared memory in a much more detail. So if you are interested in CUDA, I would suggest looking at these programming guides. So that's all I'm going to talk about CUDA. I'm now going to cover some GPU libraries, what are available, and how to call them. Our favorite slide. GPU libraries are drop-in acceleration. So most of this I will have said already, but it's worth reiterating. You want to use a library because it's easy to use, because they follow standard APIs. You know, if you are doing FFTs using FFTW, switching to QFFT shouldn't be. So QFFT is the GPU FFT library. Shouldn't be much effort. It uses a similar API. Similarly, QBLAS is similar to most. It's similar to the BLAS API. It's quite easy to implement a GPU library. They're high quality, by which we mean not only that they're fast, but they're also bug-free. And finally, they're tuned by experts. So they will be, in almost every case, faster than something you may spend weeks writing yourself. So if there is a library function available for what you're doing, I strongly recommend you use the library function rather than writing your own code to do it. They are high performance, and as I said, they will be high performance in the future on future GPUs that you may not be thinking about now, but in 5 years' time there'll be a new GPU, and maybe one of the parameters you've chosen while tuning is out by a factor of 2. So someone else can catch that, make it faster on the new GPU without you having to change any code at all. Now, GPU libraries don't cover everything. So, linear algebra, for example. Here is a bird's eye view of linear algebra. We have on the outside a solver, and then we have matrix. So solver is solving AX equals B for X. We have matrix operations, so doing a matrix-matrix multiplication, for example, and we have vector operations. There are we're going to partition this into sparse, dense, multi-node, and single-node. And already here we have 3 libraries. We have BLAS working on the matrix and vector operations, LAPACK covering solvers, and SCALAPACK covering that across the multiple nodes. And this is just in the dense space. There's more going across the sparse space, solvers, matrix operations, vector operations, single node, multi-node, and even more. So there's a lot of libraries, and a lot of these will call, several of these already support GPUs, some of whom call them under the hood. But I'm just sort of trying to say that the library philosophy is not to cover this entire space of libraries, but is to provide basic building blocks. So that a lot of those libraries, if running on the GPU, would call QBLAS. QBLAS is a low-level basic building block, which a lot of them use. The intention is to make our libraries easy to use and make them fast. When you're using a library, it's not really great if you have to focus on how to implement a fast Fourier transform, for example. You don't want to have to bother with that. You want to concentrate on your code, making your code fast. So it enables you to focus on what is unique to your code rather than having to reinvent the wheel. So the libraries that are available within CUDA, I'm just going to pick out 5, but I've put an and more on the end. So QFFT is a fast Fourier transform library. QBLAS is a BLAS library. So BLAS, for anyone who doesn't know, is vector-vector, vector matrix, and matrix-matrix operations. It's things like matrix vector products. It's dense, though, dense linear algebra, not sparse. There's CU sparse, which covers the sparse end of things. It's similar to QBLAS in that it doesn't do vector-vector operations, but it does matrix-vector and matrix-matrix operations. There's CURAND, it's a random number generation library. random number generation isn't actually a very easy thing to do in parallel, so having a library to do it for you is quite convenient. There's a NPP, which is Performance Primitives for Image and Video Processing. There's more. So there's CUDNN is one of our latest libraries, which does deep neural networks. There's AMGX, which does it's a matrix solver for using a number of different methods, not just AMG. There's quite a lot of libraries out there. You visit the NVIDIA website, you'll see quite such a breadth. Now these are all NVIDIA maintained libraries. There's third-party libraries as well. Again, visit the NVIDIA website. I don't have a slide for them. I thought I did. So going into those libraries, the ones I think will be most important for you guys. QBLAS, it's dense linear algebra on GPUs. It supports all 152 standard routines for single, double, complex, and double complex calculation. You can call it from the host. You can call it from the GPU. It doesn't matter where your data is. It can start on the GPU. It can start on the CPU, and it will work. There's also an interface for it which allows you to do computations across multiple GPUs. So matrix multiplications across multiple GPUs, for example, which can significantly improve performance. There's another extension is out-of-core streaming to a GPU. So if you have a truly massive matrix, it's no longer constrained by the GPU's memory size. It will stream data in and stream data off. So the GPU memory size for this sort of problem is no longer a limit. So I should point out level 3 BLAS is matrix operations. So all of these tend to be quite high complexity in terms of computation, but not so high complexity in terms of memory movement. So this out-of-core streaming works quite well. And there's also a drop-in implementation where you can literally not change your code one bit, change some the way some objects work, and it just works. So it intercepts the BLAS calls and offloads them onto the GPU. The standard interface, however, is a bit different, but as you can see, it's not much different. So that's BLAS on the left, CPU BLAS on the left, and QBLAS on the right, where we've essentially added a QBLAS beforehand, and we pass a handle, which is a QBLAS sort of preserved state, which is useful to have for it. In terms of performance, this is running on a K40C that goes up to about 4 teraflops single precision, about 1.5 double precision. So we can see that we're doing pretty well. So SGEM is over 3 teraflops. Complex GEM is over 3 teraflops. And when we get to double precision, we are, what are we at there? We're about 1,250 teraflops. Well, 1.25 teraflops, I should say, which is fairly close to peak. So they're doing well on performance. This is with the input data and the output data on the host, not starting on the GPU. So this is starting on the CPU. This includes the copy across the PCI bus. A comparison to MKL, we have the CPUs there, so it's a 12-core Ivy Bridge compared to a K40C. I think this was done a few months ago, so it hasn't been done with the latest processors. Or the latest version of QBLAS. But I think the general theme is there is that it's approximately 6 times faster doing this ZGEM operation than MKL. So ZGEM is double precision complex matrix multiplication. QFFT is quite a similar interface to FFTW. It supports real and complex single and double precision. So similar to QBLAS. It has 1D, 2D, and 3D batched transforms. And it's got flexible data layouts for input and output. For FFTs, it's pretty fast. So here's a graph of showing you quite how fast. So this is using power of 2 transform sizes. You can see there's a bit of a drop off here, but it peaks at about 700 gigaflops in single precision and about 275 in double precision. So that's quite fast. FFTs are a bit strange because they are not fully bound by the floating point performance. A lot of it is the 250, 300 gigabyte memory connection to the GPU's RAM. So reading and writing to RAM is often a bottleneck when you're doing FFTs. So they can't achieve quite such performance as the BLAS operations.
Do you know what the batch size is for those results?
So it's 32 million elements, and so it's 32 million elements, constant element number, and log 2 transform size is the x-axis. So the batch size will vary depending on the transform size, but it's a constant number of elements. Moving across the non-powers of 2, we can see we don't get quite the peak, but the general performance is roughly similar. Typically, power of 2 is better, but non-power of 2, powers of 3, powers of 5, powers of 7 are also fast. So using QFFT is fairly easy. Allocate our GPU memory. We create our plan, which tells the GPU what we're going to do, what data types we're using, whether we're 1D, whether we're 2D, whether we're 3D. All this information is created and put into the plan. And then we execute the plan potentially many times. So we can execute the plan doing a forward FFT or an inverse FFT. We can reuse that plan many times using the data created in step 1. And then once we're finished, we destroy the plan, free the GPU memory, and off to next our application. So the next hands-on session, I think, will cover CU-GLAS and CUFFT and calling them from Fortran. So I think that there are some slides with the presentation which should cover, with the hands-on lab, that should cover what you need to do, but referring back to these may be useful. I think it's fairly well covered in the slides for the hands-on there. So this is a C leakage, unfortunately. This is not in Fortran, this is in C, but is essentially an example QFFT program from scratch. So we have our QFFT handles, we're using complex data types. We create our plan, we do a complex transform, I've lost my mic. A complex to complex transform, and then a complex to complex transform inverse, and then we destroy and clean up.
So how much more difficult it would be to make it Fortran?
You'll see in the lab.
Okay.
So the case I've used, I believe, is almost exactly this program, but in Fortran. Running out of time, so I'm just going to flick through the last few slides. QSparse is similar to QBLAS, but for sparse matrices rather than dense matrices. So the CSR sparse matrix multiply I talked about in the last talk, that's supported in QSparse. There's other formats of matrix you can use: CSR, Q, and block matrices. There is a little demonstration of SPMV. So that's pretty much. We didn't have this section or the alpha in the code I showed in the first talk, but it's very similar. We have a sparse matrix. Most of them are zeros. CURAND, as I said, generating high-quality random number generators in parallel is tricky. Don't do it yourself. Use a library. It's got many different ways of generating random numbers. And we've got the statistical test results in the documentation to show that it does actually generate random numbers. And there's a number of different options you can use in CURAND to generate different types of random numbers with different generators. Performance of CURAND, again, this was done a few months ago. In fact, this is using a Sandy bridge, so we're perhaps a little unkind to the CPU here. But we see about 75 times faster, and that's not going to be that much less than 75 if we move that up to an Ivy bridge as well. So it's significantly faster than generating random numbers on the CPU. So there's different distributions you can generate numbers for, uniform, normal, log normal. They have slightly different performance, but it's depends on which generator you use. So to summarize our libraries, they offer high performance for minimal effort. There's a robust community of third-party libraries, which if you go on the NVIDIA website, we link to several. They're familiar interfaces, drop-in acceleration, and they allow you to focus on your core software rather than having to worry about implementing primitive operations. So that's what I've talked about. I've talked about the libraries and the language extensions. And I think that's the end of this one. So are there any questions?
Does CUDA provide a JIT compiler at all?
A JIT compiler? We did at one point. I don't know what the current support for it is, but about 6 months ago, I think we released a JIT compiler. Do you know what the current status of that is, Tim? No? Okay. So there is one available, but I don't know what its current status is.